So, hello everybody. We come to our next lecture. As we promised in our previous lecture, that the first thing to get plasma is to ionize. And how to ionize the gases? It is nothing but supplying energy. So, a time will come when the electrons will be stripped out. The amount of energy required to take out the one outermost electron from the orbit to infinity, you can say that is the ionization potential. Now, the energy that is required to take that electron out, the first ionization potential, the first electron that you want to take out, is plotted over here for all the elements up to z is equal to 80 in the periodic table. So, this data you can easily find out from any book, that what is the ionization potential. They are readily available, and if you plot, you will get such a zigzag kind of thing. So, in the peak, some atoms are situated. Like, you know that who will be there? They are the inert gas configurations, that helium, neon, argon, krypton, xenon, radon. So, they are the inert gas configuration atoms which are residing there at the top of the peaks because of their inertial configurations. But as you uh, move further in the Z line, so because of the larger and larger orbit, the electrons at the outermost orbit get less influenced by the nucleus, and so the taking out the electron becomes easier. Like you see that helium, the ionization potential, then neon, uh, argon. So they're actually coming down. Then because of this increasing orbit radius, so influence of the nucleus become lesser. So then in the same cell, when they are gradually reaching the inert cell configuration, it becomes more and more difficult to take out the electron, and that is how the zigzag kind of distribution of ionization potential that you see over the periodic table with increasing Z. Now, in this chart, where we will be most interested is basically the argon and helium. In industry, usually it is argon plasma which are mostly used to provide the inert environment. And you know why? Because if you see the composition of our environment, you see that nitrogen is the most, but a concentration of argon is more than that of your carbon dioxide. And you check the periodic, you check the your composition of our atmospheric constituents, and you will see that that is true actually. So, argon is rather easily available inert gas, and the arc or the plasma that is generated using argon is pretty stable compared to the molecular gases when you use that to generate plasma. For example, if you generate plasma using nitrogen and using argon, the discharge will be much more violent in case of nitrogen compared to argon. And of course, the hydrogen plasma is of interest. This is mainly because, you know, if you strip out the electron, just you say get one proton over there. So that is one important thing. And the other thing is that hydrogen is used in many reduction processes. So plasma chemistry requires this hydrogen for many of the applications. So basically, another molecular gas which is used is nitrogen, and nitrogen is a molecular gas, and as I told you, the discharge will be violent. But this is a very economic alternative of using argon. Nitrogen you can use a plant and you can generate very easily from the atmosphere. So it is very cheap, and the environment that it provides is mostly inert. So nitrogen is having a triple bond which is extremely difficult to break, and that is why actually nitrogen, for nitrogen that triple bond is very strong and it is very difficult to break, and that almost provide an atmosphere which is mostly inert kind of thing. But of course, nitriding can happen, but that will come to that later. So, apart from argon, hydrogen, this nitrogen plasma is also used, and oxygen plasma is used for cutting. So, this is because that kind of cut that you get using oxygen plasma is extremely smooth, almost comparable to the laser cutting kind of thing. But if you use other plasma, then that bar and that finishing of that cut is not that good. Then, apart from this, what I was saying, that argon, then helium is a very cool plasma when you generate. So, hydrogen, helium, argon, nitrogen, oxygen, so they are frequently used in the industry. Apart from that, that is air. What happens if you use air as a whole to generate plasma? The problematic thing is that air is having something which is oxidizing. And the discharge is also violent. But the positive thing is that air is freely available. So if you are able to generate plasma using air, which is not so easy, then it will be very, very economic. With this introduction, let us move to the thing that how do we ionize a gas. So for this actually, I frequently say that plasma begins with the name of Saha, because you need to ionize the first condition to make the plasma, and world begins plasma with the name of Dr. Meghnad Saha. I have shown in this a quote by Rosalind in 1939 that the impetus given to astrophysics by Saha's work can scarcely be overestimated, as nearly all later progress in this field has been influenced by it, and much of the subsequent work has the character of refinements of Saha's ideals. So, this is a wonderful equation which gives you the composition of plasma when it is in equilibrium at a temperature T. What it says, what is written at the bottom, Nr plus 1 into Ne divided by Nr is equal to 2 Zr plus 1 by Zr, then 2 pi mkt by h square to the power 3 by 2 exponential minus E ion by ionization by kT. So E ion is the ionization energy. So if you are going for fast ionization, then this will be the fast ionization potential. T is the temperature at which the plasma is staying, and this is a generic equation. That is why R is as the your index that has been used. So for example, if you are considering a plasma which is having only fast ionized state, then you just put R equal to 0. Then what you get actually, N1, that gives you the density of fast ionized state, then multiplied by Ne, that is in the numerator, then divided by N0, that is the neutral. So it is a combination of electrons, fast ionized and neutral. And then that ratio is equal to twice Z1. So that is the partition function of the fast ionized state divided by Z0, that is the neutral state, the partition function. then 2 pi mkd by h square, that you know what is that, and then the exponential term. So Saha tells that the composition of the plasma for the first ion state, it is having electrons, first ion, and the neutrals. They will follow this equation. So this, you know that Meghnad Saha and J.C. Bose and S.N. Bose, they are some of the very, very renowned people who are indispensable in the, whose works are indispensable in the scientific area. You know that Bose-Einstein statistics and in our plasma, the Saha ionization equation, they are the very, very basic things. And you know their professor is Professor J.C. Bose, and you can see this this photograph. I got it from somewhere, and you see Professor Bose is sitting in the middle, and he is surrounded by Meghnad Saha and Gyan Chandra Ghosh, and S.N. Bose is standing. You can see the collection of stars, the time the pioneers. That's why I gave the title of the slides. So we feel very proud about our Professor Saha for this Saha ionization equation, and anywhere in the world, whoever starts the plasma, they must have to start with this Saha ionization equation. Now let me tell you what is lying inside this equation. So with a concrete example, suppose let us start with triply ionized argon. Earlier I was telling only first ionized. Here, to make the thing pretty complex, let us start with monatomic gas argon, which is inert. As I told you, it is most widely used plasma gas. And we are considering a plasma, and with such a temperature that you can have the species argon atom, argon plus the first ion, argon double plus the second ion, and argon triple plus the third ion, and the electron. And what the generic equation that we just told, that Saha ionization equation, the topmost equation what is written there, that gives the three equations termed 1, 2 and 3 on the bottom left side. So from this generic equation we have derived the relation between N1, N0 and Ne in the first equation, the relation between N2, Ne and N1 in the second equation, and N3, Ne and N2 in the third equation. Now a very interesting thing about this Saha ionization equation is that you have to find out the 5 species concentration, and the concentration of argon, argon plus, argon double plus, and argon triple plus, and electron. So these are the 5 species that you need to know. But what Professor Saha has given, only 3 equations, 1, 2, 3. Then they are not sufficient to find the concentration of 5 species, because we have only 3 equations. So these 3 equations are not sufficient, but you can easily get 2 auxiliary equations to solve the problem, so that in total you get 5 equations and 5 unknowns, and that is sufficient to solve the problem. So what are the other 2 equations that we will get for this problem? So one thing is charge neutrality, that we are telling from the beginning that plasma should be neutral, because it started from neutral and it will stay as neutral as a whole. So if density of electrons is Ne, N1 is the density of the first ion, N2 is the density of second ions, and N3 is the density of third ions, then the equation 4 that is written there is Ne is equal to N1 plus 2N2 plus 3N3. Why 2N2? This is because each double ion contributing 2 electrons and each triple ion is contributing 3 electrons. So together we get N1 plus 2N2 plus 3N3, that is the total number of electrons. So get one auxiliary equation. And the fifth equation, what we have written here, the plasma that we have generated is definitely at certain temperature pressure. So for the temperature T, and if any N1, N2 and N3 are the species densities, then what you get, total pressure is P equal to Ne plus N1 plus N2 plus N3 into Kt. That is total density into Kt, Nkt. P equal to Nkt. N is Ne plus N1 plus N2 plus N3. So now what do you have? You have a complete set of 5 equations, 1 to 5, and you have 5 unknowns. So you can solve the problem very precisely. But there is one catch. In this, as you are increasing the temperature, then what is happening? One species is depleting and the other species is getting created. For example, in the first equation, you see, we have a relation between N1, Ne and N0. What is N0? N0 is the neutral. N1, where from it is coming? From N0. So N0 is getting converted into N1 and Ne is getting produced in the process. Now, suppose we have achieved a very high temperature and then this N0 is almost like 0. Then a time will come when computer will recognize N0 as 0 and then computer will simply refuse to compute, telling that you have a divide by 0 error. So that is something your numerical technique by which you can avoid the problem. So I am telling because I have solved this problem myself and I encourage you to solve this problem yourself because it is now an age of computer and you can do it easily as an exercise and you will see that this problem you are getting. So how to avoid that, I am leaving to you. You search that, find a way to get it done and it can be done. So let me show you the result that you get after solving those 5 equations. Here we have plotted the density of argon plus, argon double plus and argon triple plus together with the electrons at 1 atmosphere pressure. Now what I have plotted is not the density actually. I have plotted mole fraction because if I plot density, the physics get smeared in that actually. You will not get a very vivid picture of what is happening. You will get lots of curves and they are mingled and clumsy curves you will get and you will not get a clear picture. So that's why I chose to plot mole fraction as a function of electron temperature. Now how mole fraction is defined, that is given on the right side, that some species divided by the total number density and that is a ratio of density of a certain species divided by the total density. So that gives you the mole fraction. Now another interesting thing what I have plotted in this is the theta. Theta is the non-equilibrium parameter. It is called thermal non-equilibrium parameter. So I have plotted for theta equal to 1 where I assume that the electron temperature and heavy species temperature like ion temperature and neutral temperature, they are all same. So this is something called thermal equilibrium. I will come into detail in the later lectures. So here what I have plotted the ionization scenario when T equal to Th, the solid curve, and for Te, which is 20 times greater than the heavy species temperature. So that is the dotted curve. They are more or less following each other, bit different, and how they are a bit different that can be seen later on, and these differences become more for molecular gases and much less in the monatomic gases like argon. Let us come to what we are seeing here. You see that up to 10,000 degree Kelvin or a bit less, what we see that mole fraction of argon is almost 1. So at least at 5000 degree Kelvin, we can say that mole fraction of argon is 1. So the complete gas, argon gas, is in atomic state. They are not ionized. But as you go on increasing the temperature around 10,000 degree Kelvin, the argon curve start dropping. So the mole fraction of argon is dropping. At the same time, you follow the solid curve at the bottom, the electron is increasing. Mole fraction of electron is increasing. This is because argon, why it is dropping? Because argon plus is forming. And you see that till 20,000 degree Kelvin, argon plus and electron, they are following the same curve. And this is required to be so, because this argon becoming argon plus and it is generating 1 electron. So 1 argon plus and 1 electron. If 2 argon plus, there will be 2 electrons. So they are following the same number density. Unless and until you reach a state around 20,000 degree Kelvin, when this argon plus starts forming argon double plus. That time, 1 argon double plus is contributing not 1 but 2 electrons. So now the things become non-linear. So what happens? Then the electron density now gets separated from the argon plus density, which were being followed till 20,000 degree Kelvin. Now when this argon plus is increasing, then a time comes at 30,000 degree Kelvin when argon double plus start giving argon triple plus, the triply ionized argon. So that time you get another bump in the electron curve. So that explains how the behavior of argon ionization should be as we increase the temperature. So once we are able to fully ionize the argon, you see that we are able to do that around 25,000 degree Kelvin. So that time we are having almost a fully ionized plasma. But at that time, you see what are the species that is present over there. There not only argon plus is present, there argon double plus is also present, and argon electrons are also present. So this is how you get the composition of a plasma. Now once we get the composition of a plasma through Saha ionization equation, we get the thermodynamic and transport properties. This is basically for any thermodynamic properties or transport properties, the first thing that you require is the number density of the species. So we can say that Saha ionization equation give the kickstart to find out the plasma thermodynamic and transport properties. Why this is required? So we read about this thermodynamic and transport properties in our thermodynamics or statistical mechanics courses, but we never thought that how we can really find out these properties, thermodynamic and transport properties for actual gases like say argon or nitrogen or air or oxygen, and why do we need that? Why do we apply that? So for that actually, if we want to apply our theoretical knowledge to experimental simulation, then we need to go for this say computational fluid dynamics or any other your heat transfer calculation will require these properties. And no CFD equation, computational fluid dynamic equation, can go without this information on this thermodynamic and transport properties, because they are the quantities which define usability of any gas, usefulness of any gas, what is the potential of a plasma in certain applications, what will be the temperature range, what will be the velocity, or what will be the density, what will be the efficiency of a process, all these things basically are determined by the thermodynamic and transport properties of the plasma that we have created. So how do we get that? I have made a very simple diagram over here, and wherefrom you can see how one can find out the thermodynamic properties from the Saha ionization equation in case of plasma. You see, we get the composition from the Saha ionization equation in the first equation, so that we have already discussed at length. Once you know the number density, then you can find the density simply by adding mj nj, right? So that's a very simple thing. Then you get the specific energy in the third equation, and once you know the specific energy, then you can get the specific heats at constant volume or constant pressure. You can get the enthalpy as shown in the second last equation, right? So it is the fundamental requirement to solve the Saha ionization equation to get the values of thermodynamic and transport properties at a certain temperature and pressure of a plasma. Now you have seen that we need to have the partition functions. Here you have seen that the partition functions are involved in the Saha ionization equation, and to get the partition function you need to have the translational and internal partition function of the constituents of the plasma. And for internal partition function you need to find out rotational, vibrational, electronic and nuclear. So if the temperature is not high enough, you can avoid the nuclear part, but you need to include, if it is a molecular gas, of course, rotational, vibrational and electronic. And if it is not a molecular gas, then you can get only the electronic partition function for the internal partition function. And total partition function will be product of the translational and internal partition functions. Why I have made this slide? Because we have read all these things in our statistical mechanics or thermodynamics classes, but we need to refresh them for application in the case of plasma. So for molecules, I have listed here the internal and translational partition function. What are their explicit forms for molecules, atoms, ions and double ions and electrons. So what we have shown here, the for the molecule it is a product of this rotational and vibrational partition functions, and internal partition functions are electronic partition functions. So we need to find out what are the energy levels for the specific atom or ion or double ion. And let me clear you that for these atoms and ions, for example argon plus and argon double plus, their energy levels are different. And you know how many energy levels may be involved in one atom, and you have to count for all of them, because partition function is sum over states. So it may easily go beyond say 400 number of levels, which are usually get populated and of interest. So you need to count all of them. How you get? You can find out them in the literature. For example, there is NIST website where you can get all the energy levels if you want to calculate the partition functions. So finding out the partition functions, it is a bit laborious because you need to count for all the energy levels. So these are different your rotational and vibrational and electronic partition functions explicit form. As you can see that some of them are very standard, and the electronic partition functions that is listed there, they are already available in literature. And these energy levels, as I told, you can get from the NIST data table, also the degeneracies, whatever is G marked there. So using this you can find out the partition functions. So in the next class, what we'll do actually, how they behave, the partition functions, and how we can use them to find out the thermodynamic and transport properties in some practical examples. So I will take an example of oxygen plasma, and I will show how one can find out and what is the level of complexity one can reach to find out the properties. Okay, so this is up to this for this class, and we'll reach in the next class.